Okay, good morning, everyone. So this is our project for the 2026 Steel Awards. It is a school hall in Kuilsriffy in Cape Town or Western Cape. The school is called Brantwood. It's a full light steel frame structure. The client is Western Cape Education Department. Apologies if I'm not looking straight at the camera while I present because I'm reading off a second screen. Architects are Osmond Lang. The engineering company is By Design, and FutureCon is the contractor. So on this hall, we had previously done four school halls for the education department, but the halls that we had done previously only had a span of 18 meters, but more importantly, they also had internal walls. Because there was a couple of multi-purpose rooms within the hall as well. And we were able to use those walls to help with the structure, with carrying the load of the roof, etc. And what's actually happened, we didn't really get an architect's design up front on this hall. After we had done the first halls, we call them the first school halls, the architect team and the main contractor that runs the school projects, which is GVK, they approached us and they said, look, there's some projects coming up. They have spec'd bigger halls. They want them 800 square meters. The span is just under 24 meters. No support columns, no internal walls. Can you guys do it? So me being me, the first thing I said was, of course we can, and we'll figure out how. And then as soon as I got off the call, I phoned Byron from By Design and went, sorry, how do we how do we make this work? So we had the basic specs. So we had width and length of the building. We knew the building height, and we started the design work on that. Byron will come and talk about making the design work. But initially what happened was we had a flat ceiling and we took that design to them and they were like, great, thank you very much. But they actually want a almost inverted concave ceiling, and the ceiling is acoustic panels because it's a school hall, so it needs to follow the line of the truss. So the truss had to be redesigned to the shape that the architect wanted. But ultimately what we did is we designed, or By Design designed the hall up front, which we then took back to the architects who loved the design and essentially took it from there and drew the design onto a plan and just gave it back to us. But all the engineering had essentially already been done. We have now done, and I'll touch on it again a bit later, but we've now actually done 4 of these halls as well. So the education department love it. It works. It's a phenomenal building. I'm very excited to take the judges and actually show you, because when you stand inside the building, you get to see and feel the size and the scope of it. No one can believe that it's light steel. It's just such a beautiful building in terms of its size. Obviously now when the judges come, you can't see any of the steel. It's all hidden behind boarding and plaster and skim, but you can still feel the size, you can see the shape of the ceiling, etc. So again, I've pretty much touched on all of this. I think the big part here was design and prefabrication up front. This was a very tough site. A lot of the school sites generally tend to be in big open expanses with nothing around. They almost tend to build a school and then the community develops around it. Whereas this was a vacant piece of land right in the middle of a community, and we had to plan everything carefully, everything from deliveries, because the roads were very narrow, and there were only a couple of roads around the school and we couldn't block them. So it was all about sequencing. It was delivery. It was how to offload quickly so that the trucks could get off the roads and not block them, and then erect. The thing is, it's the irony of success, because we keep delivering for the education department, because we keep building first the smaller halls, and we've done classroom blocks, and then last year we got the award for New Orleans, which was a school rebuild. They've come to expect from us that we not only will deliver on time, but they're always chasing us with smaller and smaller schedules. So one of the options that we discussed was if we could get a crane on site, we knew we could get the trusses up fairly quickly within a day or two. But ultimately, there was no possibility to get a normal size crane to site, set it up, etc. We looked at the options of spider crane. It had the lifting capacity. One of the great advantages of light steel was the weight of the trusses. We got a spider crane to site. There's some pictures of it, and we managed to get those trusses up in a single day. We started early. We didn't even finish that late. We finished almost a normal time of the day. So nobody could believe we got 800 square meters of trusses up in a single day. Project overview, that just gives you some idea in terms of the costs as requested. But to us, it's all about innovation. It's all about pushing light steel frame to its absolute capacity, and showcasing what can be done. There's a great photo of the spider crane in action. He got there, he set up, and it was all systems go. And what we had actually done is we'd arranged the trusses in sequence, that a lot of them were on the surface bed ready to go up, but we did know we would get to a point where we wouldn't have the space to pick it up off the surface bed with the trusses overhead. So the last few trusses had been placed just outside the building, but the spider crane was able to move quickly, and it literally fit through a double door, which was great. That's just a picture of it pretty much finished. So on top of the one thing we didn't really touch on in this is that the ultimate span comes to about 29 meters, because on each end there is a walkway, but those were add-on trusses. They didn't have anything to do with the main truss that was a 24-meter span. Right. Now we get to the structural framing part, and I'm very happy to hand over to Bharat so he can tell you how he works his magic to make all this happen for us.
Okay, so I think for us, we've seen many large span light steel frame trusses, but then generally that would be between existing buildings or new buildings, but buildings that in themselves have lateral stability. So I think the challenge for us to do a full light steel frame building with such a big span, the challenge was to do it in a way that you could also get the lateral stability that you needed. So we basically try to design it like a portal frame truss scenario. And to be able to do this, we needed to get depth in the columns. So we ended up with 300 wide steel columns, and that enabled us to get basically a portal frame design to work, but in light steel. So that's in essence the principle of how we approached the design, was to give ourselves some depth at our column positions, and then the connection between the truss and the column was clearly a very critical thing that we needed to get right. One of the challenges in light steel is that you're working with tech screws that in themselves actually have quite a lot of shear capacity, but the critical thing is always the bearing in your thin plate material. So we ended up having quite a lot of it was quite a challenge to get those connections to work properly, and also to be practical. I think it's one thing in theory to put stuff on paper, but then to make it executable on site is a different story. So one thing that we have the privilege of doing is our business actually has a construction arm to it as well, not doing steel work, but doing other things. But we have a workshop, so our office is right on top of our workshop, and we have a lot of pieces of light steel frame that's lying around in our workshop. And if we battle with a connection, we go down into the workshop and we take the brackets and we take the tech screws and we take pieces of light steel and we play with it until we see what works and what doesn't work. In some instances, and I think when we did the previous hall, we actually made up mock-up panels and brought them to our workshop, where us and Mitchell from FutureCon and Alice EFCO, the steel suppliers, sat together with the foreman on site and also in our workshop before the time, talked through the connections, thought through everything practically, while you can touch and feel and see exactly what things look like. So I think that was a nice sort of different to the run-of-the-mill type of thing that we normally do, is to actually physically play with the members and how they connect to each other. So at the bottom, so at the top between the truss and the column, we used what we call a portal frame type scenario, but again taking the moments and reducing them to actual forces. So we are very strong when it comes to light steel frame design to triangulate things properly, so that actual forces run in a straight line and without putting unnecessary moments on members that's not necessarily very strong in moment. Light steel frame is very strong for its weight in actual force, especially if one considers all the members interacting with each other, giving quite a lot of lateral support. So by using the principles of trying to reduce moments into actual forces, that was kind of the main driving factor of how we came up with this design. So we've spoken about the design of the top connection, and then in similar fashion we designed the bottom of the columns to effectively get a moment connection as well, which I think the next slide shows. Okay, no, never mind. But in our 300 column, we basically have in one direction load case, we have a compression in the one leg and a tension in the other leg. And when the wind reverses, it's the opposite scenario. So on the inside leg of the columns, we use chemical anchors to anchor the inside leg of the column down to the into the concrete, and then on the outside leg, we use the chemical anchor vertically, but we also use the horizontal chemical anchor going down the face of the edge beam of the concrete raft. Because we're always concerned about a chemical anchor so close to the edge of a concrete beam, but by running a vertical member down the face of the edge beam, we use that anchor in shear, which is obviously a bit gives a bit more peace of mind than using it in tension. And you also don't have that concern of it breaking out of the edge of the concrete. So that was the two key connections that basically drove the design. So in the span direction, the lateral stability came out of this deeper column and the interaction of the column with the truss and the column with the concrete floor. So that gave us the lateral stability in the span direction. And in the long direction, we used a series of bracing systems. So we had a top chord bracing system, and then we had a bottom chord bracing system. The bottom chord was LSF frames as well. The top chord, we just used hat channels because the forces in the top chord is not that significant, because it's only really picking up the depth, the top half of the depth of the truss, if you view it from the gable end. But at the bottom chord level, the forces are much bigger, because we're picking up half the height of the gable walls, the wind force of half the height of the gable walls. And that we catered for by putting 4 sets of bottom chord trusses along the length of the building. And then along the long sides of the building, wherever we had opportunity to put vertical strap bracing, we placed vertical strap bracing to bring all those forces down to the ground. And that, in essence, is how the structural system worked. Mitchell, I don't know if you think we need to elaborate more on that, but I think answering the question of what were the main sort of achievements here, I think it is the combination of a large span building with a relatively high eaves height that is laterally stable, all out of light steel frame. I think that to me is the main design achievement that we managed to pull off in this situation.
Yeah, look, absolutely. And I'm gonna run through the slides, but ultimately it's the same common theme that is throughout this presentation. Is ultimately it all comes down to the design, the spans, the wall heights, etc. I do think it's in our notes somewhere, but it is stipulated, maybe cheekily so, but it is a point to prove. Is the one thing we have in the Cape is massive amounts of wind, which puts a lot of force on a building. And we have just been through a monster storm, as everyone knows, and has seen on all the news and all the flooding and everything that we've had. And with the insane wind speeds that we get, we've had absolutely no issues on any of the buildings. So that in itself speaks for the structural integrity of the building. And yeah, it's literally all about walls and roof are all light steel and high walls and a very big span. So it comes down to, we don't have the light steel detailer with us on the presentation. He's not a member, so he's not allowed to be on this. But ultimately, it's using the FrameCAD software and going backwards and forwards with Barent. It's taking Barent's design, running it through FrameCAD, looking at any additional questions that pop up. And the nice thing is we really use all these tools. I have in the presentation, I have put a link that you can actually go to this building online in Sketchpad, and you can have a look at it and you can go through it. And while that's very cute for a presentation, it's something that we actually use on site. We're able to take our devices, we can take an iPad to site, it's easy to carry around, we can zoom in, we can have a look at different aspects of the build. So when it comes to design and the models, etc., for us as a contractor, it's very useful to have on site. It eliminates a lot of questions. We don't need to always phone Barent and ask a question of something we're not sure of. We can literally zoom into a very specific section of the design and have a look at it. Again, questions, how clashes identified and resolved. It's teamwork. It's initially sitting down and having a look at the design, where to start, how to connect it. I think a big part here is how the truss is set in the wall and not on top. And a little design aspect like that made, first of all, erection of the building very, very easy. As easy as it can be, if I can say it that way. But such a simple design concept, which from a structural point of view is important, but just from an erection point of view, to be able to do things like pick up a truss with a crane and almost drop it into place and have guys on scaffolding on each side, that the second that truss goes in to secure it, the guys know exactly what to do. Again, as Barent touched on earlier, in terms of we know what bracket's going to go in, we know how many screws is needed, we know where to put it. So the design and using a model like this is critical. Metal cladding, and I'm going to be very honest here, is there was nothing really exciting about the sheeting on the roof. Ultimately, it's a simple pitch. It might be large, but it's a simple pitch. We used Youngman spring lock. It's something that's spec'd on pretty much all the schools. The teams are used to it. We like the fastening system. I'm not going to spend much time on the metal cladding because the project to us is all about the light steel. So fabrication. So again, this is such a crucial part to us. Once we've got a design that we know works, it's all about how to execute that. The thing about this is once the detailer's model is complete, has been checked, has been sent back to Barent. Barent rechecks it, and once everyone's happy, it's such a clean environment to manufacture a building. It goes through a machine. It goes through a frame CAD machine. You can see on the right-hand side there, all the coils sitting, waiting to go in. And yeah, it basically goes through a machine. You've got a team standing there. The team are experienced. They know exactly what they're doing. Every part is numbered. Crucial, absolutely crucial for us when it gets to site. The frame CAD machine numbers every single member, and then every panel as well is numbered. So when we get to site, there is a picture a little bit later that I'll show you, where we can lay out all the panels on the slab exactly in minutes, literally, knowing exactly which panel goes where, which direction it faces, does it face in or out, which panel it connects to. So just some nice pictures of them assembling and starting to stack, getting ready for transport. So there's the picture I was talking about, and you can see how small the road is for a truck. So essentially this building came on 2 trucks. So it came, you can see how we're starting to lay out on the slab. When everything's numbered, it's easy, it's a Meccano set. So we set it up, we get everything ready. The big planning was get the walls up, temporarily brace them before the trusses come, then get the trusses onto site, lay it out, get it ready so that as the trusses come, they're in a specific order and the crane's on site, quick and easy. I know I keep saying quick and easy and making it sound like that, but it's also credits to our teams, to the design team, to our teams on site. Like I said, this was our 5th hall, but our first big hall with the bigger spans. But we have done so much light steel, and most of it is with Barent and with LSF Co. that it is a well-oiled machine. I did put that at the end of the presentation and said I thought it was a bit cheesy, but I think it's very true, and it's important when you have a team of people that are all in different companies, but that have worked together on so many projects in the steel industry, that we understand each other, we understand each other's thinking, we understand the designs. Again, that comes down to what Warren said earlier about sitting together, pre-design, during design, after design, sitting before we get to sites. It's numerous meetings, going through all the designs, Zoom calls, emails, just checking. So once the manufacturing process starts and we get to site, everybody is very clear on their role, on how everything fits together. I am watching the time. I do see we only have a few minutes left, but that's okay. I'm not going to read line for line on here. This is all prepared in detail for the judges to go through. But here's a good one. So, the benefits of steel in this project. So obviously we are the light steel section of the Steel Institute, and we specialize in light steel, but it's showing what light steel can do that traditionally could only have been done with the portal frame, with heavy steel, which would have taken a lot longer, which would have taken a much bigger crane. The weight of a traditional portal frame would have increased the raft size, and it's achieving the span with light steel, but it's also the speed. You can't underestimate how much difference on a site that speed makes. To get a building up in a couple of weeks so we can start cladding it is incredible, especially a building of this size. So I won't go through all the quality assurance and that. There is a process that gets followed all the way from Barent and site inspections, the fabrication, how the machine's calibrated every day. We're constantly talking to the factory as well if we come up with any issues, if something's out. And when we say out, we're talking a millimeter or two. That hasn't actually happened in a while. We have listed sort of the SAISC codes that we follow as well. Sustainability, I think this is something Steel Institute knows well, but especially with light steel, I think the big thing here is we have almost zero waste. It's absolutely incredible on a site. So they say here the machine cut-off waste is minimal, generally no more than 3%, which is tiny, and all of that is recycled. But when you get to site, there is not an extra panel lying around, there's not an extra piece. We probably have a couple of screws left over that go to the next project. And there is zero waste. When it comes to the steel, there is absolutely zero waste on site, which is incredible if you think about it. And when we order boards and insulation for the walls and that, it's not project specific. So, we use the same cavity bats in the walls. So if we have a couple bags left over, it just goes on to the next project. So I think that's a really big thing in terms of waste. And if you think of the amount of waste a brick building would create. Again, I think just go for it.
Can I actually say something about the waste? Something that I'm very excited about is that 3% waste that was mentioned here. I would say most of that 3% waste is this hexagonal cut-out plate that we call a shimmy plate. Yeah. And a shimmy plate is my best friend when I design light steel frame connections. Whenever we have any kind of connection, my first question I ask myself or anyone in my design team is, can we use a shimmy plate? And we actually have a couple of them lying around the office here, and we many times sit with a shimmy plate in front of us thinking, can we use this thing? How can we use it? So even at 3% waste, we use extensively in all our connections, which I think is very cool.
No, it is. It's a remarkable use of any material, in this case steel, in terms of in how little waste we actually generate. One of the last slides, I think, 47. What are we most proud of? We've touched on this over and over and over again. It's really that we're pushing the boundaries of light steel frame in South Africa. We're achieving what hasn't been done before. We're showing the whole of the construction industry, but also the steel industry. We're showing what can be achieved in light steel with spans, with trusses, and that turns into projects in terms of, when a project is so efficient, so little waste, so efficient on site, such a quick turnaround, the return on investment for the end user is huge. In this case, while money is always a very important aspect, it's a school hall. It's about the quicker you get it up, the quicker that school gets to put learners into that hall and use it for what it's supposed to be used for. And it's really incredible when we're on site, literally only for, I think from start to finish, we weren't on site longer than probably 2.5 months in total. And that's from putting steel up, cladding, rendering, putting the roof sheeting on, doing the external render, windows and doors in, floor finishes. It's crazy. Barnes, I don't know if you want to go on that as well.
Yeah, no, I think you've summed it up. I think that is the key thing. So nothing more to say on that.
Yeah, look, again, we pretty much out of time. We've got about a minute left, so I'm not going to read every slide. We have put a lot of information in here for the judges to have a look at and to read through. We put a lot of pictures into the media folder online. And we're excited about doing these sort of projects, and we want to do more, and we want to keep pushing boundaries, and we want to see how far we can take the light steel industry in South Africa. So from my side, thank you, everybody. Thank you for your time.
Yes, thank you.